Hello! If you follow the channel, you might remember that I mounted an expedition to find a box for the Apollo ground service equipment prop build. I went to Access Solutions, our sole remaining surplus store in the valley. Well, you would not expect me to return with just one box, would you? And indeed, I came back with my large SUV full of stuff. But one of the smaller and unremarkable things I picked up while I was there was this very blue dial-a-level box from the 1970s. Mind you, I did pick it up for a reason. That is, if there is any reason to pick old stuff from electronic surplus stores. I was looking for a controller to the regulation of temperature of my Apollo IRIC gyroscope. The gyro needs to be regulated within 0.5 degrees C, and that was done in the spacecraft with a simple on-off control. So I needed a box that can monitor a resistance or the voltage across it and trigger an on-off heater within a band. Actually, I really wanted something like that, an original NASA temperature controller ground service equipment. But the one I found appeared to be from the 1970s and surely had the best name ever, Dial-a-Level. So when I saw this box at Access Solutions, I thought this was the ticket. Seems to have all the required element, a big percent screen here that measures something, and a big min and a big max button, and actually there are two of them on top of each other. One is for control, the other for alarm, two alarm and control lights, and the back looks promising too. It has over there a motor or load. I suppose that's what the control does, turns on the motor or the load. The alarm seems to be controlling a relay over here, and there's a whole bunch of inputs on that side. And no screws, which is always a little bit suspicious when you buy something and the screws are missing. It means somebody has tried to repair it and failed. All the boards were without the screws too. Now I put some so they don't fall out. And you can see it's very, early 1970s electronics, but very clean. So let's see if we can make that thing work. One mystery remains though, as the input seem to have not two, but three input connections named probe, marked with three cryptic circles. These were positively identified as hieroglyphics, so my instrument is actually 4,000 years old. What a find! But very annoyingly, this might not be as simple as reading a voltage after all. Although it ended up in Egypt, it appeared to be manufactured by Expo Instruments in Sunnyvale, California, right around the corner from where I live. I could not find any info on this model, but there was a minimalistic website about the company. It confirmed that the company was started in the 1970s and specializes in liquid measurements using special capacitive sensors. Uh-oh, that might be what my three-pronged probe is for. It had a little inquiry box, so I left a useful message asking about info about my 50-year-old box, obviously without much hope of hearing anything back. Little did I know. So I came up mostly empty from my web search, but note how it says patent pending on the front panel. So I went patent hunting instead. And bingo, we found two patents from the 1970s assigned to Expo Instruments, both from inventor George Rauchwerger, or Rauchwerger I guess in English. This proved immensely helpful. The abstract pretty much says it all. The probe consists of two spaced elements, each insulated from the other and from the material whose moisture is to be measured. So here is one example of the probe in question. You can see the two electrical conductors that I am highlighting in yellow, but in reality they are insulated from the material they are in over their whole length, so they really don't touch the material that's in between them. However, they'll form a capacitor, and the value of the capacitor will depend on what material is in between the two electrodes. And the very thorough patent then goes on to give you the formula of a capacitance between two plates, which depends of course on the area of the plates and the distance in between them, but also is proportional to the permittivity of the material between them. And if you refer to permittivity relative to air, which would be epsilon 0, then for air you have K equal 1, and for water it's 81. It's 81 times stronger. So of course if you fill the thing with 100% water, the capacitance will be 81 times that of the empty thing. And it's of course proportional to how much water you have in there. So you have made a water sensor with just a very simple capacitance probe. And note that the probe is connected by what looks like a coax, but it's not a coax, it's a triax with 3 conductors in it. So it has a center conductor, which is connected to one side of the probe. It has a middle shield, which is grounded, and an outer shield that's connected to the other side of the probe. So our hieroglyphics make perfect sense now. It's a depiction of the 3 conductors in a triax cable cross-section. I bet you didn't know that Egyptians had invented triax. You learn stuff every day on this channel. And conveniently, one of the patents explain the electronics. Those are not the electronics that are in my box, but the blocks kind of resemble it, so it really helped me a lot. The principle is the same. So here you have first an oscillator, that's this portion right here. And that is just a 10 kilohertz sine wave oscillator that sends a signal into one end of the capacitive probe, then it comes back and you measure what comes out. And so here's the circuit that measures capacitance, and I thought for a second this is going to be complicated. So it takes a whole HP instrument to do it, but they don't have to measure absolute capacitance. They only have to measure relative capacitance, which is way easier. So here's your regular op-amp circuit that works at DC. You have a signal that comes here, you have an input resistor, you have a feedback resistor, and basically the output that you get here is proportional to the input, and the ratio depends on the ratio of the resistors. Well, you can do the exact same thing with capacitors. Now, of course, you have to drive it with AC. But here you have 2 capacitor impedances, and the output here will be proportional to the ratio of the 2 capacitors. So inversely, if one of the caps varies, then the signal here, the amplification ratio will vary, and the signal here will vary. So that's exactly what they do. And that's exactly what this circuit here does. It measures this capacitor versus this one. So it's really that very simple circuit. And after that, it's a super classic. You have a rectifier, that's a peak detector. So that's an op-amp with a diode in the feedback that charges a capacitor. So that will give you a signal proportional to the amplitude of this. And then there's a comparator, and then they use an SCR, a silicon control rectifier, on the output. You can see a few of these. Well, you see the power supply, and it's a symmetric, so you're going to have a plus and minus side to it. You see the silicon rectifier, and the SCR. This is actually a triac, so this one is an updated version. The oscillator circuit is here. You see the magnetics, the 2 transistors that do the oscillation. This little circuit is for the alarm. It's fairly easy to tell because it has two op-amps that do the comparator, and there's a little relay. So that's the telltale sign. And then most of the rest is in that board. And since the whole thing didn't work when I got it, I had to pull it out and reverse engineer it. And here is the circuit in question, and I was able to get the whole schematics out of it. Fills my whole piece of paper. It looks complicated, but basically it's pretty much what you would expect from the patent, except it has been further refined. So if you look at this, there's 5 op-amps which have no markings or markings that don't make any sense, so that was an additional difficulty. But here's the first one that measures the capacitance of the probe against, and that's the capacitance it's making the ratio with. So that's the feedback capacitor. Here is the one that does the peak detection, and you can see the rectifier right here, the diodes right here. This one is just a simple amplifier. It's an op-amp plus a transistor arranged as a voltage follower because it has to drive all the meters. And then you have one comparator for the minimum level, one comparator for the maximum level. So it's pretty much what I expected. So the part that was not described and got me going is this whole thing here. And it took me a while to figure out that this K1 is actually a relay. It's a read relay. You guys can look up what that is. And also it turns out that those things which I thought were transistors are not transistors, but they are also SCR, silicon control rectifiers. And that's to make a weird flip-flop circuit. So I finally figured out what it was doing by probing around with my scope. And there are two SCR thyristors, one that's hooked up to the minimum level detection and one's that's hooked up to the maximum level detection. And they actually both go into nothing, which I'll explain in a second. But what happens is that the min level, when it comes up, is not directly coupled to it, it's differentiated, so it only gets a pulse. So when it goes through the minimum, it goes high, and that will trigger this guy. Thyristor or SCR, so once it's triggered, it stays on even if it goes back to zero. So this one is on and stays on, so your control starts past the minimum. And then this guy is the maximum. So when you hit the maximum, now this guy triggers, and it's coupled to the other one via the capacitor here, which is that big giant capacitor over here. I was wondering what it was doing. And basically, since this one will become conductive, there will be a pulse traveling through here, and it will turn this one off. It'll put this one at zero. And this one won't recover because it's not triggered anymore, and this one will continue. And vice versa, when this one is triggered at the minimum, it turns off this one. So it flip-flops the control within the dead band. And the other subtlety here is that the output of the SCRs were connected to nothing. And the other coil of the relay was connected to nothing either. And what happens is that those two need to be connected, and you choose whether this side of the flip-flop or this side of the flip-flop does the control. So you have this control reversal. But if you don't have a connection, it won't work, and that's what was happening to me. I was missing the connection, and that's over here. It says control reversing. And what happens is that you need a jumper between this and that, or this one and here. But this goes to the coil of the read relay, and this goes to one of the flip-flop thyristors, and this is the other flip-flop thyristor. So right now I have it come on when it goes below min, and you can also have it come on when it goes above max. But if you have nothing there, absolutely nothing will happen. Then this thing still didn't work, and I had another fault, and this is probably the one that got the instrument junked. It was very simple. It's just the pin 1 here was not making contact. This was not pinching enough. So once I figured that out, it's pretty much started to work much better. So in order to connect the probe, I took that from another patent. So you have to put a little transformer at the end and put the capacitive probe here, and then this superimposes the signal over here. It puts it in series basically. So your measurement circuit is this, the cap. This puts the signal at the end, and you measure it over here. So here is my little audio transformer, and I'll put that should be the ground pin. The capacitor should be between the ground of the excitation, so that's the outer shield of the triax, and the output of the transformer. Measurement signal comes out and goes back to the center conductor on my hieroglyphics over here. And what I use here is it's very convenient little capacitance box. You can change it, you can make little RC circuits and change them over here. But I use just the capacitance side of it. And let's see if we got something. I think I wired it reverse. Whoop. Ooh. No, there you go. Oh, I was on very low capacitance. There you go. So low capacitance. Hey, it works. And as the capacitance goes up, you can see the signal go up. And let's try it again. Now I have hooked up the lamp as the load, so we'll see if the triac works and if I can control it. It sure does. It turned it on because, yes, because we're low. So we're below the minimum. So it turned the lamp. That's correct. And now I am going to go up. And it went past the maximum. Turned the lamp off. And then if I go back down, it needs to go below the minimum to turn it back on. So we have the two SCRs playing flip-flop with each other, which create that programmable deadband. So here we have the alarm. So the alarm can be done independently. It should be off. Why is it on? The alarm comes off before, oh, because I have them inverted. So here I'm going to put the alarm lower than the control. So control comes first, and then alarm comes on. Usually you would just have an application as a heater, or at least in this case it's more like your pump, right? So your level is fine here, so this is neither alarm nor control. Then your reservoir goes down and the control turns on to replenish the thing. If it dries really too much, you're going to get the alarm, and then it replenishes the thing, and then when it's full, the control goes off. If it's too full, the alarm goes on, and then you can dial any level. So that's basically what it is. You can also have it, if you change the jumper at the back, you can have it do emptying, so the pump will come on when it's too high and come off when it's too low. It basically does what I want. I just have to convert it, so I can do a temperature control and have it read the thermistor instead of have it read a capacitor, and it will do just fine. And now is the best of the story. Look who answered my email shortly after I repaired the thing. It's George, the inventor himself. Now that made my day. He went on to explain that he wound up his company in 2017 and gave everything he had to Access Solutions. We're still conversing as we speak. I really hope I can meet him over a beer when the COVID episode is over. And now that I have George on the horn, I can ask him all kind of questions if I did this right, and I almost did. But it tells me in this model, you actually don't need the transformer, the magnetics of the transformer. It's been improved. This would be my center coax, one side of a cap, and this would be the inner coax. So this is much simpler, no transformer, just two wires to the cap. And let's see if George is right. And yeah, it just works just as well. So I complicated the thing for no reason. It's actually a pretty neat trick. So out of its triax, it is only two conductors connected at the probe. The only one conductor connected at the probe. The two others are simply for shielding. All right. Well, thank you, George. Your dial level works perfectly.